Welcome to the Walton Pi. Today I'm going to be going through a test review that will hopefully help prepare you for a calculus test that would cover things like implicit differentiation, derivatives of inverse trig functions, derivatives of logarithms, related rates, absolute maximums, absolute minimums, local maximums, local minimums, critical points, inflection points, the mean value theorem, and things like showing that there's exactly one solution to a specific equation. Okay? If that's the sort of thing that's hopefully helpful, let's just jump right on in, and hopefully we'll be able to explain all of these so that you can be able to have an idea of what sort of things you need to study a little bit more on. The way I would recommend studying for this test is to just do a bunch of problems. So before watching me do any of these problems, pause the video right after I've written down the problem and try it on your own first, because that's going to be a lot more helpful for you than just following along with me. Okay? So, and if you need to watch some other things on other topics, feel free to check out a bunch of my other videos. I've made several videos on most of these topics, so hopefully one of those would be helpful for you as well. Okay, so to get started, let's do the following. So let's find dy dx if we know that we have the relationship tangent of xy minus e to the y is equal to y cubed plus sine of x minus y. Okay, so we have this situation and we are trying to figure out what is dy dx. Go ahead, pause the video and try and figure it out on your own first. So the way that I would recommend doing this is to just take the entire expression and just take the derivative of everything. And this is going to be the implicit differentiation part. So we're going to just take the derivative with respect to x of the tangent side, and we are going to set that equal to the derivative with respect to x of the other side. And now for each of these pieces, what we're going to be doing is we're just going to use implicit differentiation, which is essentially just the chain rule. Anytime we take the derivative of a y, we are going to have a dy dx pop out. So the derivative of tangent, well, that's going to be secant squared. We have secant squared of the inside, xy minus e to the y, but then we have to multiply by the derivative of the inside. That's the chain rule. So the derivative of xy, that's going to be x dy dx plus 1 y, so that's the product rule on xy, and then minus e to the y, derivative of that goes to an e to the y times a dy dx. And there we go. That is that entire side of the equation. So we have that, and now let's take the derivative of the other side. Well, derivative of y cubed, that's 3y squared dy dx. Derivative of sine is cosine, so we have cosine of x minus y multiplied by the derivative of x minus y, that's a 1 minus dy dx. Okay, at this point what I would recommend doing is multiplying things out so that we have dy dx terms and non-dy dx terms. So when we multiply all of that out, we get a secant squared xy minus e to the y times x minus e to the y dy dx plus y times secant squared of xy minus e to the y. So that's that entire side. And then this side, the dy dx terms are, we have a 3y squared and a minus, what is going on today? Okay, 3y squared minus dy dx, whoops, minus 1, and all of that is times dy dx. And then we have a cosine of x minus y term without a dy dx. And now what we're going to do is we are going to move all the terms that have a dy dx to one side, and all the terms that don't to the other side. So what we're left with is we get secant squared of xy minus e to the y times x minus e to the y dy dx minus 3y squared minus 1 dy dx is equal to cosine of x minus y minus y secant squared of xy minus e to the y. What we can do with these terms is we can pull this dy dx out from both sides, and then what we are left with, we can then factor that out. So let's do that real quick. So when we factor that all out, that will be dy dx times all of that, and then we can divide all of that over to the other side to find that dy dx is equal to cosine of x minus y minus y secant squared of xy minus e to the y, all divided by secant squared of xy minus e to the y times x minus e to the y minus 3y squared plus 1. And there we go. That is the entire derivative of dy dx. Okay, so now we're going to go on to a related topic where we are going to be finding the derivative of inverse trig functions. Okay, so find the derivative of y equals inverse secant of 4x minus 7. Okay, so the first thing that we're going to want to do is we are going to want to rewrite this so that we know how to take the derivative of each piece. Now, the inverse trig functions, those are really complicated ones to remember. I can't keep them straight, so the way that I would recommend doing this is to rewrite this expression as secant of y is equal to 4x minus 7. And now we are going to take the derivative exactly like we did on the first problem, where we are going to be using implicit differentiation. So when we take the derivative of all of that, what we're going to be left with is derivative of secant. That's a secant tangent, so we get a secant y tangent y multiplied by the derivative of the inside. So that's a dy dx, and that's going to be equal to the derivative of 4x minus 7, that's 4. So we get that dy dx is equal to 4 divided by secant of y tangent of y. Now, this is not where we want to stop. The reason for that is we were given an expression in terms of just x's, and we have the derivative in terms of just y's. We don't want to do that. That's turning in a paper to your French class in English, or turning in something to your English class and all you did was write everything in Morse code. Yes, that's technically the answer, but it's not a helpful or useful answer. So we want everything in terms of x. So we need to figure out what is secant of y and what is tangent of y. Well, the nice thing is we already know what secant of y is. Secant of y is 4x minus 7. So we can get rid of part of this, but we still have that tangent piece we have left to deal with. So we have 4 divided by 4x minus 7. But what is the tangent? Well, here's where we're going to go back to early trig stuff when we were talking about all of that, and we have this sort of triangle thing. We know that we have some angle, y, and we know that secant of y is 4x minus 7. Well, what is secant? Well, secant, that's 1 over cosine, and cosine's adjacent over hypotenuse, so that means that secant is hypotenuse over adjacent. So that means the ratio of our hypotenuse to our adjacent side has to be 4x minus 7. So if we label the hypotenuse as 4x minus 7, then the adjacent side is going to be a 1, and now we need to know what's the opposite side. Well, the opposite side, remember, these are the sides of a right triangle, so we can use a squared plus b squared equals c squared, where c is the hypotenuse, so that means that we get 1, because 1 squared is 1, plus whatever we have squared needs to be equal to 4x minus 7 squared. Well, if we just subtract the 1 over, then that means we can just take whatever this is just going to be the square root of that. So we are going to have this last side be the square root of 4x minus 7 squared minus 1. Now tangent, remember that's sine over cosine or opposite over adjacent. So tangent of y is this opposite side divided by the adjacent side. So it is going to be just the square root of 4x minus 7 squared minus 1. And that is going to be our derivative. Okay? Hopefully that made sense. And if it didn't, try some other problems. Just smack whatever other sort of inverse trig functions you want together, stick some stuff in the middle, and there you go. You're able to create a whole bunch of different things to be able to tie all of it together. Okay, now let's look at if we have some trig functions, not trig functions, logarithms. So this one is going to be asking us to prove that the derivative with respect to x of the natural log of x is 1 over x using implicit differentiation. Alright, so if we have this, how would we do that? So if you think you know, pause the video, try and figure it out. If you don't know, still try and figure it out, because that's going to be the best way to do it. But if you don't know, go ahead and watch me go through this all together. So we're going to set this up very similarly to the last one, where we have y equals natural log of x, which is the same thing as saying that e to the y is equal to x, and then this is something that we can then take the derivative of with respect to x. So the derivative of e to something is e to something times the derivative of that same something, and then the derivative of x is 1, so we put all of that together. Then that means that dy dx is equal to 1, I am really struggling with my screen today, so 1 over e to the y, but we know what e to the y is. E to the y is x, take that, plug it in here, so we get the derivative of y is just 1 over x, so that means that the derivative of the natural log of x is 1 over x. Okay, let's do another problem. This time we are going to be doing some sketching of graphs, and we are going to be trying to do a whole bunch of stuff with one function. Okay, so for this problem, I'm going to ask you to find the absolute maximum, absolute minimum, any local maximums, any local minimums, any critical points, any inflection points, any increasing regions, any decreasing regions, anywhere where this function's concave up, anywhere where this function's concave down, and we are going to be looking specifically on the interval from 0 to 8. Okay, so go ahead, pause the video, try and do all of this on your own first. Okay, so to get started, for absolute maximums, those will happen either at critical points or on the boundaries, which means that in order to do that, first we're going to need to find the critical points. Well, how do we find critical points? That is where the derivative is equal to 0. So first, we have to take the derivative. So the derivative is going to be 3x squared minus 30x plus 72, which we can actually factor pretty nicely. This factors as 3 times x squared minus 10x plus 24, which is 3 times x minus 4 times x minus 6, which means that we have critical points at x equals 4 and x equals 6, both of which are inside our domain, so both of which are going to be places we're going to have to check. And so now what we're going to do is we need to figure out what is the absolute maximum and absolute minimum. And to do that, what we are going to be looking at are the places where we're going to be looking at y of our critical points, so y of 4, we need to look at y of 6, but then we also need to look at our boundary, so that's y of 0 and y of 8. So as we go through each of these, let's see what this is equal to. So this is 4 cubed minus 15 times 4 squared plus 72 times 4 minus 13. So that is 64 minus 15 times 16. Let's see, that is 50 plus, no, 500 plus, one sec, let's see. So 16 times 15, that's 160 plus 80, so that's 240. Plus 72 times 4, that's 280 plus 8, so 288. Minus 13, which is, let's see, 240, 288, that becomes a plus 48. Let's see, 48 minus 13, that's 35. So 64 plus 35 is 99. There we go. So y of 4 is 99. We now look at y of 6. Let's see, so y of 6, that's 6 cubed minus 15 times 6 squared plus 72 times 6 minus 13. 6 cubed is 216 minus 15 times 36. So that's 400, let's see, 15 times 36. 540 plus 72 times 6. Let's see, 72 is 2 times 36, so that's 30. So 6 cubed times 2, so that's 432. 432 minus 13. So let's see, adding all of those things up together, what does that become? So 216 plus 432, that's 648. And then we have minus 553, which is 95. Yes, that is 95. Okay, so there we go. Y of 0, plug in 0 everywhere, that we just get minus 13. And then y of 8, that'll be a little bit harder. Y of 8, that is 8 cubed minus 15 times 64 plus 72 times 8 minus 13. There we go, let's see. We get 8 cubed, that's 64 times 8. That's so 64 times 2 3 times, so 128, 256, 512. 15 times 64. 64, so that's 960 plus 72 times 8. 72 times 8, that's 16 plus 560, 576. Minus 73, which is 100 and something. That's 115. Yep, okay. So the absolute maximum is the biggest of these numbers. So biggest of 99, 95, negative 13, and 115. So the absolute maximum value is 115, which happens at the point 8, 115. And then the absolute minimum value is negative 13, which is at the point 0, negative 13. So both of our absolute maximums and minimums happened to occur on the boundary. But then we also have a local maximum, which is what happens at those boundaries. So we have a local maximum at the point 499, and an absolute minimum at the point 695. We have our two critical points that we've already found, but now we need to know what are our inflection points. So we're going to need to know what's our derivative. So we're going to need that again. So let's write down that first derivative again. So our first derivative was 3x squared minus 30x plus 72. Oh. It's all coming back. Okay, so the first derivative was 3x squared minus 30x plus 72, which means that our second derivative is 6x minus 30. So our inflection points are where is the second derivative equal to 0, which is nice. It happens at x equals 5, which means that the actual point itself is going to be 5 f of 5. We need to actually figure out what is the value of the function at 5. Well, that's going to be 5 cubed minus 15 times 25 plus 72 times 5 minus 13. So that's 125 minus 15 times 25. That's... Okay, let's just do that real quick. I'm not good at mental arithmetic. So that's 375 plus 72 times 5. That's 360. Minus 13. Let's see, 375 and 360, that's minus 15 together. So that's 125 minus 28, that's 97. So it's at the point 597. There we go. Now the question becomes, where is this function increasing? So for where it's increasing, what I would recommend doing is have some sort of number line and label your critical points. So our critical points are 4 and 6. And now what we're going to do is we are going to be looking at the first derivative, and we are going to look to see is it positive or is it negative in the different spots around there. So remember, our function y prime, that was factored as 3 times x minus 4 times x minus 6. And all we care about is the sign. So let's plug in something that is smaller than 4. So let's just plug in 0. Well, y prime, that's going to be equal to 3 times negative 4 times negative 6, which is going to be a positive value. We don't care about the specific number, we just care what's the sign. Okay, so there we go. That's going to be a positive number. But then if we plug in something between 4 and 6, such as 5, then when we plug in that number, what we get is 3 times 1 times negative 1. So that's negative. Because we have one negative and two positives, multiply those together, we get a negative. And if we plug something in bigger than 6, like say 8, then what we would have is when we go through and plug everything in, we get 3 times 4 times 2, that's all positive. So when we're asked where is it increasing, well, it's going to be increasing from 0 to 4, and then again from 6 to 8. And then if we're looking for where is it decreasing, well, that's going to be on the interval from 4 to 6. And the reason I'm not going from negative infinity to 4 and then 6 to positive infinity is because our domain is the closed interval from 0 to 8. Now, when we're asked to find where is it concave up and where is it concave down, we do a very similar thing to what we just did, except instead of looking at the critical points, we're going to be looking at our point of inflection, which is happening here at x equals 5. So now we're going to look at the second derivative, but we're going to be plugging in numbers bigger and smaller than 5. So maybe 0 and 8. Well, when we plug in 0, we get negative, and when we plug in 8, we get a positive. So that means when it's negative, you're feeling down, you're going to frown, and that's concave down. So it's concave down on the interval from 0 to 5, and then it's concave up on the interval from 5 to 8. Okay, so now the question is, how would we graph this? Now that we have all of those different pieces of information, let's graph this function. Because this might be something that we would be asked to do on a test. So here we go, interval from 0 to 8. We don't need the full axis because we're only going 0 out to 8. So here we go. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now how would we graph this? Well, let's start by plotting any points that we know. Okay, so we know we have an absolute maximum value at 8 when it's up here at 115. So let's go up by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 115. Here, let's just, there we go. Now we can actually go up. Let's move that up there. Okay. Alright, so 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. Okay, so at 8, up here at 100, okay, and then minus 10. So up here at 8, it's at 115. There's one endpoint. Alright, now we can try and see everything again. Okay, there we go. And we have an absolute minimum at 0, negative 13. So there we go. We have our 2 points that we know about. We also know we have a local maximum at 4, 99. So that's going to be happening up here. We have a local minimum at 6, 95. We have those are our critical points. We have an inflection point at 597. And now we are going to have to connect up all of these different things. So we know it needs to increase, and it's going to be concave down on the first section. So that means it's increasing but concave down. And now it's going to decrease and be concave down. Now it's going to decrease and be concave up. And now it's going to be increasing and concave up. And there we go. That would be our rough sketch of what this function would look like. Okay, so now that we've done that, let's jump into a related rates problem. So, here we are. Our nightmare situation. We have become the math problem. Okay? So in a fit of anger, after seeing the ridiculousness of all these different questions that I'm asking you, you decide to track down my address at 314 Euler Road in Mathlandia, and you decide to cover my property with toilet paper. However, just as I have planned, the things that I've been asking you and explaining to you have begun to seep into your mind as you start to throw the toilet paper. So you notice that you can throw the toilet paper exactly 15 meters per second, and that gravity is exactly 5 meters per second squared. You're still not entirely sure how that's possible, since you know that on Earth it's like 4.9 meters per second squared, but somehow I've managed to distort the gravity around my property, and so you're not entirely sure how gravity is exactly 5 meters per second squared. But you do just somehow know that that's what it is. You're not entirely sure how you know, but you know? Okay, so on a whim, because you are becoming your own worst nightmare. Who wants to go and do this? But on a whim, you measure the toilet paper, and you realize it has a diameter of 13 centimeters, and that there are exactly 40 sheets of toilet paper that stack together to be 1 centimeter thick. You shrug and okay, I don't need to know this. I could just put that out of my mind, and you start to throw the toilet paper anyway. And then suddenly, tragedy strikes. Exactly 2 seconds after you threw the toilet paper, you ask yourself, how fast is the diameter of the toilet paper shrinking right now? And then you pale. Oh no. I have become the math problem. So, unable to move, you decide, I need to solve this, and then I need to get out. I need to get out of Mathlandia before I become the person who's buying 1 million watermelons and trying to figure out how to stuff them in a car. We need to solve this problem and get out as fast as we can. So, how fast is the diameter of the toilet paper shrinking? Now, we're assuming that the toilet paper is unraveling as it gets thrown, and the way that we're going to assume that it unravels is that as you throw the toilet paper, there we go. So as you're throwing the toilet paper, so here's the toilet paper roll, it's unraveling, we have part of it, and we are going to assume that the very bottom of the toilet paper, that is always on the grassy lawn at the very bottom. So as you throw the toilet paper up, it's going like this, but the toilet paper is unraveling, so it's always touching the ground. Okay, so that's how we're going to be setting up this problem. So how do we solve this? We're going to need to try and figure out what exactly is going on. Okay, so somehow this is going to connect to some sort of related rates. There's different things interconnected. How do we solve this? Okay, so let's try and figure out a few different things. We're going to need to break this down into a few different pieces. First, what we're doing is we are starting by throwing the toilet paper straight up at 15 meters per second. And then this is 2 seconds later. So 2 seconds later, it's at this height. And now what we're trying to do is we're trying to figure out what's going on. So the first question we might ask is, how fast is the toilet paper traveling after 2 seconds? So let's approach that problem first. So let's slide on over and try and figure out what's going on. So we have our diagram. It's going up, and then we are trying to figure out what's happening. Well, we know that gravity is equal to 5 meters per second squared, and gravity, that is an acceleration. Which means that we need to go through and figure out, well, if gravity is 5, and I know that the derivative of velocity is acceleration, what's a function whose derivative is just 5? Well, I'm going to say that my velocity as a function of time is going to be equal to the original 15 meters per second squared times the time. Well, let's see. So it's 15 meters per second. Oh, it was, yeah, just 15 meters per second. That's how fast I originally threw it, but then gravity is going to be slowing it down. So I'm going to then be losing 5 meters per second every second. So that means my velocity as a function of time is going to be 15 minus 5t. Okay, so that means we can now know what's the velocity at the time we care about. Well, the velocity at the time we care about is 2 seconds. So that means the velocity at 2 seconds is going to be 15 minus 5 times 2. So that's 15 minus 10. So that is going to be equal to 5. So at this specific instant that we care about, it is moving upwards at a velocity of 5 meters per second. And we also are going to need to know, how high up is it? Well, remember that the derivative of position is velocity. So that means we need to have a function whose derivative is 15 minus 5t squared. Now, that's going to be a little bit tricky, so I'm just going to give it to you. The position as a function of time is going to be equal to 0 plus 15t minus 5 halves t squared. Don't worry if you don't know how to do that yet. That is going to be what we're going to be talking about in a couple weeks when we are going through stuff with antiderivatives. So don't worry about that yet, but that's what we have currently. So what we can do is we need to know what's the position at time t equals 2. So our position at time 2, that is going to be equal to 15 times 2 minus 5 halves of 4. So that's going to be 30 minus 10 is 20 meters. Wow, you got a really good arm if you're able to throw it that high. So there you go. 20 meters is how high up it has gone. So now we've figured out the position of the toilet paper roll. Let's go back and try and figure out what else are we going to need. Alright. We're going over here back to our question. So there we go. We have all the different things that we need. We are trying to figure out all of the different stuff left that we need. So we can throw the toilet paper at exactly 15 meters per second. So we've accounted for that in our picture. Gravity is exactly 5 meters per second squared. We've accounted for that. But now we're trying to figure out, how can we figure out how fast the toilet paper is shrinking? So what do we need to do? We are going to need to somehow relate the rate that the diameter of the toilet paper to something else. Okay? So now here's how we're going to be doing that. We know how much toilet paper has been pulled out. We know it is 20 meters long. And we also know how much it was originally. So now how are we going to figure out exactly how long it was? Well, here's going to be the little bit of trickiness that we're going to have to figure out. So, come on, so let's draw a toilet paper roll real quick. So here we go. We got our toilet paper roll, and we have a whole bunch of different sheets inside. Here we go. We got a whole bunch of these sorts of things. There we go. So now what we're going to do is let's label these different things. We have a few different squares of toilet paper that are here, and toilet paper, I actually did measure this, is 10 centimeters across. Diameter is 13 centimeters, so all of these are the actual dimensions. And now what we're going to do is we're trying to figure out how much of the toilet paper has come off. Well, we know that the total distance is 20 meters, so what's the volume of that toilet paper? Well, the volume is going to be the 20 meters by 10 centimeters, and then the thickness is going to be 1/40th of a centimeter thick. So let's convert everything to centimeters. So that's going to be 2,000 centimeters, and so the volume that has been taken out is going to be 1/40th times 10 times 2,000. 2,000 divided by 40, that is going to be 50. So 50 times 10 is 500. So the volume is 500 cubic centimeters that has come out. And now the question is that all of the toilet paper? Well, let's figure out what's the original volume of the toilet paper. So volume of a cylinder is going to be not 4/3, that's of a sphere. So volume of a cylinder is pi radius squared times the height. In this case, the height is 10. Radius is going to be half of 13, so that's going to be a 6.5. And then a pi. So volume is, and we're going to say that pi is about 3 just to get a rough idea. And because of the inside piece, let's just round the 6.5 down to 6. So volume is about 3 times 6 squared times 10. 3 times 36 times 10. 36 times 3, that is 108 times 10. So that's 1,080 cubic centimeters. So we did not use up all of the toilet paper, which is good. Okay. So now what we're going to do is trying to figure out how fast is the diameter of the toilet paper shrinking. So let's go, and that was just a rough calculation to make sure we didn't use up all the toilet paper. Now we're going to need to know what is the current radius of the toilet paper. So the current radius of the toilet paper is going to, I'm getting ahead of myself. So we're trying to figure out the rate that the diameter of the toilet paper is shrinking, which means we need to have some sort of connection between the diameter of the toilet paper and the height that it's up, because the height directly connects to how much of this toilet paper has been pulled off. And so let's go and tie those different things together. So let's just take this a little bit slower. So the volume is equal to pi r squared times the length, which is going to be the 10. So volume is 10 pi radius squared. We want to have some sort of connection to diameter. Diameter is 2 times the radius, so we can then say that diameter over 2 is equal to the radius. So we can use that here to get that the volume is going to be equal to 5/2 pi diameter squared. So now we have some connection between diameter and volume. But we also know how much volume is going to be used up. We know that the volume of the toilet paper that's been pulled out, so volume of our strip versus volume of the cylinder. So the volume of the strip that's going to be equal to our height times 10 times 1/40th. So this is equal to h over 4. So there we go. We have some sort of connection between the volume of the strip and the volume of a cylinder, and we know the connection between both of those together. We know that the volume of how much toilet paper has been pulled out plus the volume of how much toilet paper is still in the roll has to be equal to the original amount of toilet paper that was there, which is equal to the pi times radius 13/2 squared times the length, 10. So we know for a fact that is how much there needs to be, which means this is a constant, we have a connection with height, and we have a connection with diameter. We can tie everything together. So let's put all of that together. So we know that, let's see, 10, so we know that pi times 13 squared, that's 169, times 10 over 4, so that's the total volume. That has to be equal to 5 pi over 2 diameter squared plus the height over 4. Okay, here's where we're going to be able to tie everything together. We know how fast the thing is going up, which is telling us how fast h is increasing. So we know it's going up at 5 meters per second, which is 500 centimeters per second, which is how fast h is changing. That's the derivative of height with respect to time, which means we can now get a connection to the diameter, which I'm going to now just change to be a capital D, just so that we don't have a little bit of confusion with that. Okay, how do we go through and do it now? Now what we're going to have is we need to find a connection, and the way we do this is through implicit differentiation. We are going to take that expression that we just found, namely that 1,690 pi over 4 is equal to 5 pi over 2 d squared plus h over 4. And we're going to take the derivative of everything with respect to time. Now notice that the original volume actually all just cancels out when we take the derivative, and that just goes to 0. But then when we take the derivative of the other side, we get 5 pi over 2 times 2d dd dt, so that's a d dd dt, plus 1/4 dh dt, and we know what dh dt is. So that means that 0 is equal to 5 pi d dd dt plus 1/4 times 500. Okay, that means all we need to know now is what's the diameter at the specific time we care about. And to do that, that is going to be going up to our original equation, which we actually just wrote right here. So that means we also can solve for what d is. So when we solve for d, we know what height is, so we know that 1690 pi over 4 equals 5 pi over 2 d squared plus the height in centimeters is 2,000 over 4. 2,000 over 4, that is plus 500. Okay, so that means that d squared is equal to 1690 pi over 4 minus 500 all over 5 pi over 2. So d squared is about, let me pull up a calculator and figure this out, because I'm not going to want to do this exactly. We're just carrying approximate. So let's see, here we go. What is that number? So 1690 times pi divided by 4 minus 500. So that is 827.3 divided by okay, here, let's just actually just write the whole thing at the end. Okay, so divided by 5 pi over 2. 5 pi over 2. D squared is about 100. is about 105.34, which means that D is about 10.26. Okay, so there we go. We have the diameter at that specific instant. So we can take that and plug it in, and we can solve for what dd dt is. So 0 is equal to 5 pi times 10.26 dd dt plus 1/4 of 500. So that's 125. So that means that dd dt is equal to minus 125 over 5 pi times 10.26. Let's figure out what that is, and then that gives us what dd dt is. So we get, let's see, it is a minus, okay, minus 125 divided by 5 times pi times 10.26. That is negative 0.7756 centimeters per second. So it is shrinking pretty quickly, which makes sense because you chucked that toilet paper at a ridiculously high speed. So all of that work was to answer how fast is it shrinking right now? Well, it's shrinking at 0.77 essentially centimeters per second. That is how fast the toilet paper is shrinking at this specific instance. Okay, I hope that made sense. I hope you enjoyed that problem as much as I did, even if it was probably a little bit harder than we needed it to be, but I thought it was a pretty fun type of problem. So yeah. Okay, so for this next problem, I'm going to ask you to prove that there is only one solution to the following. To 2 cosine of x plus 7x equaling 4 sine of x minus x cubed minus 3e to the 4x. Prove that there is only one solution to that. Okay, so the first thing I would recommend doing is to rewrite this so that you have a function equals 0. So we are going to say that f of x is equal to, we got 2 cosine x plus 7x minus 4 sine x plus x cubed plus 3e to the 4x, and that is equal to 0. So, if you are ever asked, prove there is only one solution, the way to do this is break this up into two things. Use the intermediate value theorem to show that there is one or more solutions, and then assume that there are two or more solutions and show that the mean value theorem gives us a big problem. And then because we get that big problem, that means there can't be two solutions, which means there is only one solution. So, first thing is we are going to say that f is continuous and differentiable everywhere. And the reason we are doing this is we need the continuity for the intermediate value theorem, and we need the differentiability and continuity for the mean value theorem. So now that we have that, we can now use both of those theorems together. So the intermediate value theorem. So since f is continuous, and let's look at some points. F of 0 equals 2 times cosine of 0, that's a 2, plus 0 minus 0 plus 0 plus 3 equals 5 is bigger than 0. So there we go. We have something that's bigger than 0. And let's plug in some really small number. So f of negative 10 equals 2 cosine of negative 10 minus 70 minus 4 sine of negative 10 minus 1,000 plus 3e to the negative 40. So let's see, 2 cosine of negative 10, that's between negative 2 and 2. Negative 4 sine of negative 10, that's between negative 4 and 4. But then the negative 70 and the minus 1,000, that's really, really big negative number. And then the 3e to the negative 40, that's close to 0. So that whole thing is less than 0. So by the intermediate value theorem, there is at least one solution. So there we go. We have at least one solution, which means that there is either one solution, which we want, or there are two different solutions. And if there are two different solutions, that's going to be how we would be able to use the mean value theorem. So we are going to use the mean value theorem, assuming there's two different solutions, and show that that is not possible, which means there has to be exactly one solution. That's how we're going to finish this problem. So now, let's use the mean value theorem. I'm going to rewrite the function. So we have f of x is, we got 2 cosine x plus 7x minus 4 sine x plus x cubed plus, what was the last part? 3e to the 4x. Plus 3e to the 4x. Okay, so now we're going to say that assume there are two different solutions. So assume a less than b are two different solutions. We just need them to be different. I'm just going to say that a is the smaller one. Okay, then f of a equals f of b equals 0. So by the mean value theorem, since f is continuous and differentiable, so since f is continuous and differentiable, there is a c where f prime of c equals f of b minus f of a all over b minus a, which is just equal to 0. So that means somewhere the derivative is 0. But f prime of x equals derivative of cosine, that's a negative sine, so that's minus 2 sine x plus 7 minus 4 cosine x plus 3x squared plus 12e to the 4x is strictly bigger than negative 2 plus 7 minus 4 plus 0 plus 0, which is bigger than 0. Because negative 2 sine x, that's between negative 2 and 2, so the smallest that can be is negative 2. 7 is just always 7. But then the 4 cosine x, that's always between negative 4 and 4, so the smallest that could be is minus 4. 3x squared, that's always bigger than or equal to 0. And 12e to the 4x, always positive, so it is always bigger than 0, which means that everything we got, all of that, is at least 1, which means it's definitely bigger than 0, which means that there can't be two solutions. And that's how we would finish. So there cannot be two solutions. And so if there aren't two solutions, that means there is exactly one solution. We don't know where it is, but we know that there is exactly one solution. There we go. That's how you would go through and do this problem. Okay, let's do another problem. Prove that the absolute value of cosine of 4a minus cosine of 4b is strictly less than or equal to 4 times the absolute value of b minus a. Okay, how would we do this one? Well, first things first, what I would recommend doing is rewrite this a little bit and recognize that we have cosine of something minus cosine of something, and we have a b minus a. So that means we're probably going to either be using a limit definition but there's no limits anywhere, so that's unlikely. Or we're going to be using the mean value theorem, which is a little bit more likely. And notice that we can switch the order of subtraction inside absolute values, because that's just the same as multiplying by a -1. So what we really have is this is equivalent to saying cosine of 4b minus cosine of 4a all over b minus a is less than or equal to 4. Well, notice that this absolute value is just the absolute value of the entire top over the bottom. So cosine 4b minus cosine of 4a all over b minus a. There we go. Well, what would happen if we dropped those absolute values? Well, then that means that we might be getting negative numbers. So that's the same thing as saying we might go as small as -4, less than or equal to cosine of 4b minus cosine of 4a all over b minus a is less than or equal to 4. What does this represent? Well, notice that if we want to use the mean value theorem, we have a function of b minus function of a over b minus a. So what's that function? So that means we have our function is just cosine of 4x, and the mean value theorem says the derivative anywhere has to be equal to that somewhere. So f prime of x, well, that's going to be equal to minus 4 sine 4x, sorry, and that's always between -4 and 4. Which means that the derivative of our function f of x anywhere has to be between those things, which means no matter what we put in, that's going to have to be the case. So that is how we would be able to show that in this sort of situation. That is -4 is less than or equal to f prime of c anywhere, which is equal to, by the mean value theorem, cosine of 4b minus cosine of 4 over b minus a is less than or equal to 4 if f of x equals cosine of 4x, which is exactly what we wanted to be able to show. So that's how we would go through and do this problem. Okay, and now for the last type of problem that you might see on a test, well, the last type of problem I'm going to go through. Use any of the resources that your teacher has provided, see what other types of problems there are, try a bunch of your homework problems, but the last one that I'm going to go through and do is to do the following. What is the largest and smallest values of f of 7 if we know that f of 1 is 6 and f prime of x is, and f prime of x is always between 3 and 7 for all x. Well, this is also a mean value theorem, because we know that f prime of x is somewhere between, well, any values we pick. If we pick the number between 1 and 7, it's going to have to satisfy the mean value theorem. So that's going to be equal to f of 7 minus f of 1 all over 7 minus 1. So that's going to be equal to f of 7 minus 6 all over 6. That has to be less than or equal to 7 and greater than or equal to 3. So if we go through and solve this for what f of 7 can be, that's how we would go through and do that. So that means we get 18 is less than or equal to f of 7 minus 6 is less than or equal to 42. Add 6 to both sides, or all three pieces. We get 24 is less than or equal to f of 7 is less than or equal to 48. And there we go. That is the smallest and largest values that f of 7 could be. I hope this video was helpful. If it was, please check out some of my other videos. I'll attach a few other videos here on the end screen that you can be able to go and watch if you would like to see some other things to be able to present to prepare for your test. I hope you have a great rest of your day. Good luck with all of your math, and good luck on studying for your test.